So welcome to this session. In today's session in the linear algebra, we will go through the following topics. So one is the rank of a matrix. So one is rank of a matrix, and other one is the given vectors are linearly independent or dependent. Then what is a vector space and how to find base as well as dimensions. And more importantly, two types of inverses we will discuss. So Murray-Penrose inverse of a matrix, or simply MP inverse of a matrix, or Penrose inverse of a matrix. So other one is generalized inverse of a matrix. So these two are a little bit new to most of us. So we are familiar with respect to how to find the inverse of a matrix by using our regular way. So these two are a little bit different and new to us. So we'll proceed. What is the rank? So this is one of the important concepts we need to understand, based on which many of the concepts we can understand very easily. So what is rank of a matrix? So various definitions. One is first is row rank of a matrix. So if we take a matrix, so we know, right? So these are row 1, row 2, row 3, like this, right? And these are all column 1, column 2, column 3, like this, right? So how many rows are linearly independent? That is, maximum number of rows which are linearly independent. We'll see what is meant by independent. So the maximum number of rows or vectors which are linearly independent. So that is called as row rank of the matrix. Similarly, with respect to columns, that is maximum number of columns, right, which are independent. So that is called as column rank of the matrix. And if these two are equal, so row rank of the matrix as well as column rank of a matrix, right, are equal, then it is called as rank of a matrix. Right? Right. So where generally we can write as rank of A or row of A. So we can write represent either by this way or this way. Right? So this is the basic definition. And how to find the rank? We'll see various methods are there. Right? And one or two points related to rank of a matrix. Right? So that finally, if we say rank of a matrix equal to 2 or rank of a matrix equal to 3, what does it mean? So it indicates the number of independent rows or columns in a matrix. Right? Suppose if we say rank equal to 2, rank of a matrix A equal to 2. So what does it indicate? The matrix may be of order 3 by 3 or 4 by 4. If we say rank of that matrix equal to, it indicates that this matrix is having 2 independent rows or two independent columns. Okay. So what is the use of matrix? So it helps us in many ways. One is the rank of a matrix helps us to find the number of dimensions that is spanned by all the vectors. That is one use. And many are there. One is to find the nature of system of equations. So the rank of a matrix helps us. And some of the observations, if rank of a matrix equal to 0, the meaning is all the vectors in the matrix span a point. That is one. If rank equal to 1, then all the vectors in the matrix spans a line. Third one is if rank equal to 2, that means all the vectors spans two-dimensional plane and so on, three-dimensional plane and hyperplane, hyperdimension, higher dimensional plane, etc. So this is the basic introduction or definition related to rank of a matrix. And how to find this? Now with one example we see, if suppose A is a matrix, so 1 0 0 1. Now as per the definition what we had, so what we say, the maximum number of linearly independent vectors. So now we know this is nothing but this vector 1 0, this is 0 1, right? Now we know these two are linearly independent. Right? That means this vector both are linearly independent. That is, two vectors are linearly independent. So therefore rank of this matrix is 2. Okay? Now one more observation that we can have is this is identity matrix of order 2. So then rank is 2. So another example. So this is what we discussed, right? So another example in the same way, if we go for similar matrix, so identity matrix of order 3. So that is here 1 0 0 0 0 1 0 0 1 0 0 1, right? So 1 0 0. So this is the first vector. 0 1 0 second vector. This is third vector along z axis. So these three vectors are linearly independent, we know, right? That means this vector, this vector, this vector, all the three are linearly independent. Therefore, rank of A equal to 3. That is one way that we define. So the rank gives the number of independent rows as well as our number of independent columns, or vice versa. The number of independent rows or independent columns gives the rank of a matrix. So other way how to find is various ways as mentioned. So suppose if we find data of this matrix, so that is not equal to 0, that is not equal to 0, then rank is equal to order of the matrix. So order of the matrix is 2 by 2, right? That is not equal to 0, therefore rank is 2. So here for this is a matrix of order 3 by 3. If we find determinant, hope that we know how to find the determinant. Otherwise, I will share some links which you can go through it. Okay. This is a basic requirement to understand rank of a matrix. Okay. Next, data of this matrix is not equal to 0. This is a matrix of order 3 by 3. Right? Order 3. Therefore, rank is 3. Now, but how this is not that easy to, it is not that easy to use this definition to find the rank of a matrix. So then, so another definition, another way of defining is the order of the highest non-vanishing minor. Right? The order of the highest non-vanishing minor is called rank of that matrix. So minor means what? It is nothing but a kind of determinant. Now, so if we take this matrix, so this is a matrix of order 3 by 3, right? So what is the highest minor, highest determinant or highest minor we can have? The determinant itself, right? So data of A. See, data of A is the highest minor. It is a minor of order 3 by 3. Suppose like this we can have, right? Suppose if we take this submatrix, right? This is one. If I take the determinant of this submatrix 1 2 2 3, so this is another minor of order 2. Similarly, if we take this, So this is a submatrix. If we take data of the submatrix, it is another minor of order 2 like this, right? So what they are saying, the order of the highest non-vanishing, highest. So now in this case, the order of the matrix is 3 by 3, right? So we have to search from the determinant or the minor of order 3. So first what we do is we will find the data of the matrix here. If it is non-vanishing, that is non-vanishing means not equal to 0, then obviously the rank is the order of the minor, that is 3. If it is equal to 0, then rank cannot be 3. That means the minor of order 3 is becoming 0. Then we have to go back and see whether it can be 2 or not. We'll see it. So in this case, first what we do is we'll begin with determinant of A. So how to do this? So I assume that we know how to expand the determinant, otherwise 1 into, so 1 into its corresponding minor. So leaving that row and leaving that column, whatever the submatrix we get, its determinant. Right? 1 into 3, 4, 1, 2. So minus, because it is minus 1 power I plus j, where it is first row and second column, 1 plus 2, 3, therefore minus comes here. So 2 into leaving that row and leaving that column. So what we get, 2, 4, 3, 2, right? That plus 3 into, here it is the minus 1 power 1 plus 3, therefore positive. Plus. So leave that row and leave that column, what we get, this submatrix, right? So data of this submatrix. Okay. Then, so 1 into is AD minus BC, right? 3 into 2 minus 4 into 1, 2 into 2 minus 4 into 3, 2 into 1, 3 into 3. Right? So if we expand, then we get minus 3. So minus 3 not equal to 0. Right? That means for this matrix, we had a minor of order 3, which is the highest, and it is not becoming 0. So therefore rank becomes 3. So in simple, if data of a matrix is not equal to 0, then rank becomes equal. Right? This is not equal, then rank becomes equal to the order of the matrix or order of the determinant. So very important. So now suppose if it vanishes, what happens? Right? One example. Right? So same here, we took a matrix of order 3 by 3. Right? So what is the highest minor possible from this matrix? That is the det itself, right? The det itself, det of the matrix itself. Right? So which is of order 3 by 3, right? So first we'll find determinant in the same way. So 1 into leaving that row and leaving that column. So whatever is there. So submatrix and its determinant. So minus 2 into the submatrix and determinant plus 2 into its submatrix and determinant, and we get it as 0. So that means the highest minor is of order 3, which is vanishing, right? But what we are looking for is non-vanishing. If it is vanishing, then rank cannot be 3. Right? If rank cannot be 3, then what to do is we have to go down next. That is whether rank can be 2 or not. So when we can say rank can be 2, if there exists a non-vanishing, that is not equal to 0 minor of order 2. Here we will have many 2 by 2 minors, right? This is one minor, this is another minor, like so first, for example, we'll take this 1, 2, 2 minus 1. 1, 2, 2 minus 1, AD minus BC. Right? AD minus BC. 1 into minus 1, this is not becoming 0. Right? That means there exists a minor of order 2 which is not equal to 0. If not equal to 0, obviously rank becomes equal. Next, suppose a question comes, if this is equal to 0, then what to do? Then we have to check for all possibilities, right? Another 2 by 2 minor is there, right? This is another 2 by 2. That we have to check. If it is becoming 0, we have to check another 2 by 2 minor. If all are becoming 0, then we have to go down and say rank equal to 1, because it is a non-zero matrix. For a non-zero matrix, rank is always greater than 0. Okay? But there is a complexity here. Complexity means it is a small matrix, very easy to do all these things, right? If it is a 4 by 4 matrix, suppose imagine 4 by 4 matrix. So first we have to try with determinant of order 4, right? If it is not equal to 0, like we are lucky and we say that rank equal to 4. Suppose if it is equal to 0, then we have to go down to 3 by 3, right? So we have to 3 by 3 means we will have many possible combinations, right? For all possible combinations, we have to check whether it's becoming 0 or not. If it is not becoming 0, 1 is enough. If it is becoming 0, we have to go down to another one, see whether it is becoming 0 or not. Right? Suppose assume that all 3 by 3 minors are becoming zeros. So then rank cannot be 3, right? Then we have to go down to 2 by 2. So from this 4 by 4 matrix, we have to see for all possible 2 by 2 minus, whichever is not becoming 0, at least one is not becoming 0, then we stop there and say rank equal to 2, right? So this is a complex procedure, right? So theoretically, to begin with, to understand, this is the approach we'll have. But so the approach what we use in when we apply this rank of a matrix is so converting into one form called as echelon form. This is one of the important methods. So what we do is we convert the given matrix into some form by using row operations, only row operations, only row operations. So no column operations, no to column. That is very important to remember. So only row operations. So we have to convert this into a matrix into one form that is called as echelon form. So what is this echelon form? So what is that form is? So now we know this is the principal diagonal elements, right? This is the called as principal diagonal. By using row operations only, so we have to see that we have to try to make all the elements below this principal diagonal elements are zeros. We'll try to. Right? Okay. So once we arrive at, we are able to get echelon form, then the number of non-zero rows is called as the rank of a matrix. So we'll see it. We'll see with this example. Now, so consider this matrix. So as discussed, now what we do is we'll try to make this as 0, this as 0, right? Okay. How to make this as 0? So row operations. Now, so this is R2, right? R2 minus 2R1 if we take. So 2 minus 2 becomes 0, right? So that's why one operation we preferred is R2 is. This is not unique. It depends on how you take, how you do. Similarly, we want to make this as 0, right? So with R3 is, right? R3 minus 3R1. R3 minus 3R1. So here it is clearly given how the operations on R2 is 2, 3, 4. And R1 is 1, 2, 3 multiplied by 2R1. And if we subtract 2 minus 2, 0, 3 minus 4, 1, 4 minus 2, that is 0. And next, so making this 3 as 0, then the operation is R3 minus 3R1. Right? So R3 is, row 3 is 3, 1, 2. So 3R1, 3 ones, 3, 3 2s are 6, 3 3s are 9, and subtracting we get this. Okay. Now whether to stop here or not, now if you see here, so this is the principal diagonal elements, right? So these two became 0. Now, so we have to make this as 0. Okay. So how to make this as 0? So now if I go for operation with R1, then this becomes non-zero, which we don't want, right? So then we will go for operation with this R2, that is R3 minus 5R1. Right? Now if you see here, minus I think, right? So R3 minus 5R1. Right? So then we'll get this. Same way with, so what we have done is, so with the help of this, using an operation, we try to make this as 0. Now if you see here, So principal diagonal and all elements below it are zeros. Okay. So then we say this is called as echelon form of the matrix. Once it is in echelon form, then so this is called as a non-zero row because not all are not zeros. So here all are not zeros. Here all are not zeros. This is called as a non-zero row. This is called as a non-zero row. This is called as a non-zero row. So therefore rank is number of non-zero rows. Here three non-zero rows are there, right? Therefore rank of the matrix is 3. So instead of going for the basic definition of the rank, so it is very easy if we go for echelon form of the matrix. So one more example we try. So with the help of echelon form. So 1, 2, 2, 2 minus 1, 4, 3, 3, 6. So this is the principal diagonal, right? So first what we do is we'll try to make these elements as zeros. So what are the operations? So this with this R2 minus 2R1, right? R3 minus 3R1. Right? So then you can write it clearly and try. So R1 as it we are not going for any operation. R2 minus 2R1, 2 minus 2 0, minus 1 2 into 2 4, 1 minus 4 minus 5 like this. So this is second operation. Similarly third operation. Now again we see here. This is a principal diagonal elements, right? Diagonal element. So this we want to make it as 0. So as discussed, it is not with R1, we go with R2, right? So here actually to make it very simple, what we tried is, so we divided the second row by minus 5, first row by 3. Right? So then becomes 1 and 1. Then R3 minus R1 operation we tried here. So here one more operation we tried, that is second row is divided by minus 5 and third row is divided by 3 to have simplicity, simple values. That is the only reason. Otherwise directly we can go for 5R3 plus 3R2. So then this becomes 0. Now we can see here. Right? This is the principal diagonal where all the elements below it are zeros. So that means what we said, we arrived at echelon form of the matrix. Once we are having the echelon form of the matrix, immediately what we see is, so we understood this is a non-zero row, this is a non-zero row, but this is a zero row. Why this is zero row? All the elements in the row are zeros. Therefore rank of the matrix is number of non-zero rows. Number of non-zeros are 2. So that means what we, another way, like earlier when we started we defined like a number of independent vectors, linearly independent vectors. Now from this we understand that because rank equal to 2, then we are having out of these 3 vectors, through 2 are linearly independent. What are those vectors? We'll see when we go further. Right? So I hope that's clear, right? So one more example here. So actually one more example. This is not a, whatever we tried till now is a matrix which is of square matrix. Here if you see, it is a matrix of order 3 by 4. It's a matrix of order 3 by 4. So same thing, right? So here principal diagonal is not, it won't go like this. So principal diagonal is 1 1 2 2 3 3. This is. So 1 1 2 2 3 3. Right? So here first similarly I will go through quickly. So trying to make this as 0, trying to make this as 0. Same like R2 is R2 minus 2R1 and R3 is R3 minus 3R. So then we got this. So you see here, this is the principal diagonal. Right? So next what we have to do is we will try to make this as 0. Right? So for which we go for operation R3 is R3 minus R2. Right? So then we get this. You see here. This is the principal diagonal where all the elements. Okay. So now same comes. So then this is in echelon form. Then rank of the matrix is number of non-zero rows. So this is a non-zero row. This is a non-zero row. But here it is a 0 row because all the elements in this row are zeros. But we are concerned with this only. So rank is 2. Okay. That means so 2 vectors are linearly independent. Okay. So this is how we can find rank of a matrix, right? So either if it is a simple matrix, we can try with the basic definition, that is with the help of determinants. Otherwise, we can try with echelon form of the matrix. Okay. Some properties which are useful. Suppose if A is a matrix of order m by n, that is a rectangular matrix, right? Then rank of A less than or equal to minimum of m comma n. Right? Suppose if you see this example, 3 by 4. So here we cannot have rank as 3, right? We cannot, because we cannot have number of non-zero rows as 4, right? At max 3, right? At max 3 non-zero, because here 3 is max, right? So that is here. So rank of a matrix is minimum of, here in this case, 3 comma 4, the previous example. So that the maximum value that rank takes for this matrix is 3 only. 3, then it comes down to 2, it comes down to 1. If rank of A equal to minimum of m comma n, here it is less than or equal to, right? If it is minimum, then we call that rank as the full rank. Right? So in the previous case, 3 by 4 is the order of the matrix, right? If rank equal to 3, then we call 3 as the full rank of the matrix A. Another one is rank of A equal to rank of A transpose. So A transpose we know, right? So what is meant by A transpose? Suppose if we had a matrix, the row 1, row 2, row 3, row 4. If we change rows into columns, so if first row becomes first column, second row becomes second column, third row becomes third column, that is called as A transpose. So rank of A equal to rank of A transpose. Then why it is so is, if we go for the basic definition, we took the help of determinant, right? And we know determinant of A is equal to determinant of A transpose. So obviously, or it follows rank of A equal to rank of A transpose. Next, 1 or 2 observations. If A is a matrix of order m by n, B is a matrix of order n by p, then we'll have the product of these two, A into B. Right? So then rank of that matrix is less than or equal to minimum of rank of the first matrix, comma rank of second matrix. This is. Suppose if AB are matrices of same order, that is m by n, then if we take the addition, we'll get a new matrix, right? Rank of this matrix, new matrix, is less than or equal to rank of A plus rank of B. Right? So these are some properties or observations related to rank of a matrix. Okay. So with rank concept in mind, we'll go with vector space. So what this definition is important. Vector space, what is a vector space? Let VNF be a set of n components. So it is VNF is a combination of vectors, right? So with 2 properties. One is sum of 2 vectors is also in VNF, right? So if we take VNF, it's consisting of vectors, and if you take 2 vectors x1 and x2 from this, okay, and if we take is closure, actually what we call as closure with respect to addition operation x1 plus x2. Right? So if this is also in VNF, this is also a vector. Next, second one is scalar multiplication. So if you take a scalar, any scalar k, and you take any vector in VNF, if you multiply the scalar by a vector, so whatever the resultant, right, the product or resultant is also in VNF. So that means two properties. One is it satisfies closure property with respect to addition of vectors. Second product is scalar multiplication, right? Multiplication by a scalar. So then VNF is called as vector space. So definition is very important in most of the examinations. Okay. Now if you want, we can take an example, right? So x is a vector 1, 2, 3, y is another vector minus 1, 0, 3. So this is a vector of order 3, vector of order 3. So this is vector of order 3. Now we'll check two properties. One is the closure with respect to addition, right? X plus y. So x plus y, first vector, second vector, then 1 minus 1, 0, 2 plus 0, 2, 3 plus 3, 6. So this is also another vector of VNF. This is also third order vector. Therefore, it belongs to VNF. Second property, take some scalar. Some scalar means some constant value, right? K equal to 4 is a scalar. So then, suppose if you multiply k by x, k is 4 multiplied by x. 4 ones are 1, 4 ones are 4, 4 twos are right 4. So this is also another vector of order 3, which is again in VNF. So that means scalar multiplication, it is vector addition is closed, and also scalar multiplication is defined. So therefore this is called as a vector space, right? VNF with the two vectors x and y is called as a vector space. So very important to have understand definition as well as an example associated with it. In most of the exams they will ask for it. So vector subspace, it is like a regular definition, right? What is meant by a subset. Similarly subgroup. Okay. So let VNF is a vector space. So this is a vector space. So vector space means immediately we remember the two properties we discussed, right? One is the closure x plus y belongs to VNF, and other one is the scalar multiplication kx is also in VNF, right? So immediately we remember this VNF is a vector space. Immediately we understand these two properties are satisfied. So now suppose S is a subset. So S is a subset of VNF. And if S also is a vector space, if S is also a vector space, that is, if S also satisfies these two properties, that is, for any two vectors x1 and x2, x1 plus x2 is also in S, and for a scalar k, ks is also, right? So very simple to define subspace. S is a subset of a vector space VNF. Right? Subset, and S is also a vector space. S is also a vector space, then S is called as subspace of VNF. Right? Very simple. Subset and also vector space, then it is called as subspace. I hope that's clear. So next, another important thing, in most of the times this question on this comes in examination. Most of the times, right? So what is a linear definition or a problem associated with this definition? Right? So consider some vectors, the basic definition: x equal to x1, x11, x12, so on, x1, and x2 is another vector like xk. And suppose there are some constants C1, C2, so on K, Ck. Right? If there exists a vector which is of the form C1 x1 C2 x2 plus so on Ck xk, right? So then this vector x is called as linear combination of. Very simple. So we had vectors, right? Suppose if we take a vector 1 1 2, this is one vector. Suppose another vector some 2 1 1, another vector. And what is a linear combination of this for a constant C1 and C2? Two vectors are there, one constant C1, 1 1 2 if you are able to write, plus C2 into second vector. So this is called as linear combination. So, combination of all these vectors which are linear in nature. That's why this is called as linear combination. Right? So this is a general definition. x1, x2, so on, xk are k vectors. c1, c2, ck are constant. Then c1 x1 plus c2 x2 plus so on ck xk is called as linear combination of the vectors x1, x2, x3 and so on xn. So based on these two very important definitions, one is linearly dependent vectors and linearly independent vectors. So just now we saw, right, let x1, x2, so on xk are vectors, c1, c2, so on ck are scalars. Then we had a linear combination, right, c1 x1 plus c2 x2 plus so on ck xk. This is the linear combination what we call as. Right. Here if this linear combination equal to 0, right, implies if at least now c1, c2, so on ck are unknowns and they are constants, right? If at least one of these constants are not equal to 0, right, are not equal to 0, then what we say that they are linearly dependent. So that means one vector is dependent on the other, etc. Then comes the other way, right? Suppose if all becomes 0, that means c1 becomes 0, c2 becomes 0 and so on, all the constants are the scalars what we selected, c1, c2, so on ck, all are zeros, then they are called as linearly independent vectors. So linearly independent, that is same here, right? So x1, x2, so on xk are their k vectors. Then corresponding scalars are c1, c2, so on ck, and it's a linear combination c1 x1 c2 x2 plus so on ck xk equal to 0. Right? So this implies c1 equal to c2 equal to 0. That means all scalars are the constants are zeros. Then they are called as linearly independent vectors. Now to understand this in a better way, suppose if we take x1 equal to the simple example which we started when we discussed rank of a matrix 1 0 0 1 0, x2 is 0 1. Right, these two are two vectors. Now we want to check whether these two vectors are linearly independent or not. Right? So first thing what we have to do, we have to write it's a linear combination, right? c1 x1 plus c2 x2, right? This is the linear combination which is equal to, we'll write this equal to 0. So c1 into, so I'll write transpose so that it will, here writing is becomes very easy. c1 into 1 0 plus c2 into 0 1, right? Now if we simplify this, what we get? So how to simplify this? So a corresponding element c1 into 1, the first element, c2 into 0, that means the first element what we get is c1, right? And c1 into 0 is the second element plus c2 into first, c2 into next. That means what we get is c1 comma c2 equal to 0. 0 means it is 0 0, right? Now what we understand here, C1 equal to 0 and also C2 equal to 0. That means whenever this linear combination is becoming 0, we are getting C1 comma C2 equal to 0. That means all constants or all scalars are becoming zeros. That means these vectors are independent vectors, right? So then if you go back and see the first definition what we tried, right? This is so 1 0 0 1, right? So they are linearly independent vectors. Similarly, this same way if we try with C1 into this first vector, C2 into the second vector plus C3 into the second vector, then what we get, C1 comma C2 comma C3 equal to 0. That means all these three vectors are linearly independent. Therefore rank is also 3. So this is very important in examination. So one example we'll see. So consider a vector C1 1 minus 1 3 and x2 is 1 1 1. So first immediately what we have to do is, two vectors are there, we have to take two constants and we have to write its linear combination and equating this linear combination equal to 0. Then C1 into the first vector. You can write either the vector as it is or we can take the transpose of this. So C1 into the first vector or first met 1 minus 1 3, C2 to 1 1 1, right, equal to as usual 0 matrix. Now simplify this. So C1 plus C2, so minus C1 plus C2, 3C1 plus C2. So now C1 plus C2 equal to 0, minus C1 plus C2 equal to 0, 3C1 plus C2 equal to 0. Now we want C1, C2 values, right? So we have to solve this. So very simple here in this case. If we add 1 and 2, we'll get C1 equal to 0. When C1 equal to 0, C2 is also 0, right? Substituting C1 equal to 0 in any one of the equations. So that means our linear combination equal to 0, so implies all the constants, that is constant C1 as well as C2, both are 0. Therefore they are linearly independent. Right? So very important this. So now one more. So find whether the following vectors are linearly independent or dependent. So 1 2 3, 3 minus 2 1, 1 minus. So here this is nothing but they gave it as a transpose. This is stands for transpose. Now same right here, x1 is one vector, x2 is another vector, x3 is another vector. So three vectors are there, right? We have to write its linear combination with three constants or three scalars. Right? So that is c1 x1 plus c2 x2 plus c3 x3 equal to 0. Right? So c1 into first vector. So 1 2 3, so you can take as it is or transpose. So C1 into one first vector, C2 into second vector, C3 into third vector equal to 0. Very simple. Now C1 plus 3C2 plus C3. 2C1 minus 2C2 minus 6C3. So 3C1 plus C2 minus 5C3. So all are zeros. Equal to 0, 3 equations. Now next, what is the next step? We have to solve these two to find what are the values of C1, C2, C3. So there are various ways. We will go for the basic way of solving the system of equations. Okay. So here the basic approach we tried. So how we solve in general, how we solve system of equations, right? Generally 1 2 3. Okay. So first we solve taking 1 and 2, we eliminated C1. I think you can go through it. It's a very basic school math. So multiplying first equation by 2 and subtracting, that means eliminated C1, we got equation. Similarly from 2 3 we got equation in C2 C3. So solving these two equations, that is we are luckily here we got one equation C2 plus C3 equal to 0. Right. So then C2 is minus C3, substituting this in any one of the equations or any of the equations, we'll get the C1 plus 2C2 equal to 0. Okay. right? First what we tried is we try to eliminate C1, then we got an equation. Here luckily both are the same. Otherwise what we have to is similarly with the help of another combinations we have to arrive at another equation involving C2, C3. That means we'll get two equations with two constants. On solving it we get C2, C3 values. Right? So various ways of solving. Right? So you can try with whatever the way that you are comfortable. So, but here in this case, C1 plus 2C2 equal to 0 is one combination. C2 plus C3 is another combination here. So here at least to satisfy these two equations, they should not be at least either C1 should not be 0 or C2 or C3. Right? Okay. So therefore, that means at least either of these three constants are not equal to 0. There are therefore, so the vectors are linearly dependent. Right, this is how we try problems related to linearly dependent and independent vectors. Next, subspace. So very simple, the set S of all linear combinations. Right. So like very simple. So VNF, right? So VNF is a vector space consisting of many vectors, right? Right, x1, x2, x3, right, and so on. And if we take a set S, so if a S is a set consisting of all possible linear combinations of these vectors, right, then S is called as the subspace. Now another very important definition is basis and dimension. So this is very important with respect to definition as well as problems also. Right. So what is a basis? Right. A set of vectors is said to be a basis. So here the carefully observe a set of vectors. Set of vectors is said to be basis of a subspace S if the subspace S is spanned by the set of vectors. Right? So what are the vectors that are there in the S, they should span it. And more importantly, what are the vectors that are there in the set, they all are linearly independent. Right? So one is, first important condition is linearly independent, and second one is it should span all the vectors. So then the set of vectors is called as subbasis. So another one is dimension. So once we had a basis of a subspace that is as discussed, consisting of linearly independent vectors, and the vectors are vector spans. So then the number of vectors in the subbasis, how many vectors are there in the basis, it is called as dimension. Right? So very important here, try to understand these two definitions, basis and dimension. So in a simple sense, very simple, right? Basis is nothing but set of linearly independent vectors in general, in simpler sense. And dimension is the number of linearly independent vectors. How many linearly independent vectors are there? That is dimension. Now how to find it? Okay. So very important for many of the examinations. Suppose V4F, that is fourth dimensional, dimension 4, is a vector space spanned by vectors x1, x2, x3, x4. So then find the basis and also dimensions. Right? Okay. So what is the approach? So here vector space we had V4 with these vectors. Right? Now we have to find this a set of vectors ES, right, which forms a basis. Where now if you remember, SC is nothing but a set of vectors, right? Set of vectors which satisfy the condition. What are the conditions? Particularly for important condition is linearly, it should contain linearly independent vectors. Next, spans. Okay. right? So first thing is we have to find the what are the vectors which are linearly independent. Once basis is there, dimension is very simple. How many elements are there in the S? So three linearly independent vectors are there. Then it is dimension is 3. Right? So this is the procedure to find basis and dimension. Right? So next the question comes, how to find linearly independent or not. Right? So same like what we discussed, right? So rank helps us. Rank helps us. So many ways are there. If we depend, if you refer the textbooks, some authors go for some kind of approach. Finally, each are the same, equivalent. So first we can take the matrix with all vectors. 1, 1, 0. If is this is x1, this is x2, this is x3, this is x4. So we have to find the rank. So remember rank. So with the help of echelon form, because here echelon form helps us, not any other. Yeah. So this is principal diagonal and these elements. So already these are zeros. We have to try for this. So what is the operation here? R2 is R2 minus R1. And then we got this. So but still here if you see, is there any possibility? No, right? So that means now we had echelon form of the given matrix. Then we, as discussed, this is a non-zero row, this is a non-zero row, this is 0 row. So then this is 0 row, right? So what is the rank here? Rank equal to 2. Number of non-zero rows, number of non-1, 2. This is a 0 row which we don't want. That means out of these four vectors, 2 are linearly independent. Right? These 2 are linearly independent. So now what are those 2 vectors, right? That is the next question. Okay. So here, if you remember how we took x1, x2, this is x3, and this is x4, right? And this is what we got, right? Now we see the principal diagonals. Right? So wherever the principal diagonals are non-zeros or pivots, generally what we call as 1, right? So here S, this is a linearly independent vector. So this is another linearly independent vector. Here it is no, right? Similarly it is not. So 1 minute. So that means what? X1, x2 are linearly independent vectors out of the 4 vectors given. So therefore our basis contains only these 2. So basis contains our x1, that is 1 1 0, and x2 1 minus 1 0. Right? So this is the basis. That is the set consisting of linearly independent vectors. These 2 are linearly independent vectors. Now how many linearly independent vectors are there? 2. Therefore dimension is 2. So this is how we find basis as well as dimension. Right? If you remember here, to find basis what we require, right? Rank. How can we have? We will have echelon form, right? So if we know the echelon form, then we can find the rank. If we know the rank, then we can say we can talk about linearly independent vectors. Once we are clear with independent vectors, then we can write basis. Right? That's why the topic which we discussed at the beginning, echelon form, is very important to do this. So it's another observation. So sometimes for a small questions like this, simply if it is possible for us to have a determinant that equal to 0, then the vectors are linearly dependent. If not equal to 0, then they are linearly independent. Right? So one more problem we'll try with respect to basis and dimension, because it is very important. Take any exam, you'll find a question on this. Right? Basis and dimension. So here 4 vectors: alpha 1, alpha 2, alpha 3, alpha. So immediately we have to remember what to do in this case. First we have to write the matrix A with alpha 1, right? Alpha 2, alpha 3, alpha 4, right? So then we have to try for echelon form of the matrix, right? So once echelon form of the matrix is there, then we'll know the rank of the matrix. So from the rank we can find how many vectors are linearly independent. Then go back and see echelon form of the matrix, from which we can find what are the vectors which are linearly independent. So once it is there, we can write the basis. Once basis is there, we can write dimension, right? Okay. So now we see here. So we'll try with, so the alpha 1, alpha 2, alpha 3, alpha 4. Right, see here. So now we'll try to make this zeros. R2 is R2 minus 2R1. Then we got this. So next, again the same you see here. So we'll try to make this as 0. So for which we go for R3 minus R2. So while doing, you may get many doubts. So make sure that once we make these as zeros, better to avoid any operation which makes these as non-zeros again. Right? Prefer go some other operation where there won't be any disturbance with respect to these two, which are already zeros. So R3 minus R2 try. Right? So now we got this. Right. Okay. Next. So this is what we got now. So this is an echelon form. Without any doubt, we can say this is an echelon form, right? Right. So then rank is 3. Right? Rank is 3. Then what are the rank? That means 3 vectors are linearly independent out of the 4. What are those 3? So here if you see here. So 1, that is alpha 1, that is alpha 2, alpha 3 no. This is alpha 3, right? And alpha 4. Right? So where this element is non-zero, right? So this element is a pivot element. So therefore alpha 1, alpha 2, alpha 4 are linearly independent vectors. Therefore this is the basis. Once this is there, so 3 linearly independent vectors are there. Therefore dimension of this is 3. Right? So basis as well as dimension. So very important, we need to try 1 or 2 problems until we understand the concept very clearly. So one more to just quickly we'll go through one more problem to understand linearly dependent as well as independent. 2 vectors are given. We have to check whether these vectors are linearly dependent or independent. So very simple, C1 alpha 1 C2 alpha 2 equal to 0 equations will get. On solving equations we'll get C1 equal to 0 as well as C2 equal to 0. Therefore they are constants, all scalars or constants are zeros. Therefore they are linearly independent vectors. Right? Next, some definitions. So if already we have been discussing VNF, right? VNF. So where F is the set of real numbers. Suppose if you take F as a complex numbers, that is n-dimensional vector space VNC over the field of complex numbers. We know complex numbers, right? That is numbers which are of the form a plus ib, right? Right? Where right? So where the vector space where the F is the set of complex numbers, where its inner product is defined. You will see what is meant by inner product. Where its inner product is defined, then it is called as a unitary space. Right? So very simple, VNF, where F is the set of complex numbers, where the inner product of 2 vectors is defined. Right? So then that VNF over complex numbers is called as unitary space. If vector space VNF, right, VNF, and it is redefined on the field of real numbers with inner product of vectors, then it is called as Euclidean space. Right? Right? So by right here VNF VNF over real numbers, right? So vector space over real numbers, it is over complex numbers. This is what we, and in both the cases the inner product is defined. Inner product is defined. In case of real, that vector space is called as Euclidean space. So in case of VNF over complex numbers where inner product is defined, then it is unitary space. Some definitions which are useful for short answer kind of questions in any of the examinations. Unitary space, right? So vector space, set of real number over a set of real numbers where inner product is defined, Euclidean, over complex numbers where inner product is defined, unitary space. So inner product. So what is this inner product? Suppose x, y are two vectors, right? Over the V and C, that is where f is nothing but here complex number set. Then x star y, x star y, where star is transpose conjugate, that is Hermitian. That means suppose conjugate means if I'll write here, if I take a complex number x plus iy, right? And its conjugate is x minus iy. If x plus iy is a complex number, x minus iy is conjugate, or vice versa. X minus iy is complex, then its conjugate is x plus iy. So now what it says is take its conjugate and transpose, then it is x star, and its product with y is called as inner product, right? If it is over a set of real numbers, this conjugate won't be there, right? Simply it becomes a transpose, right? X transpose y is called as the inner product space if it is over a set of real numbers, right? Very simple here. Suppose x1, x2, so on xn, y1, y2, y3, so on yn are two column vectors. That means this x1, x2, y. Then x star y. So here, so we have to take conjugate and transpose of x. Conjugate means where we have to write conjugate of x1, x2, x3, so on xn, and take the transpose. So transpose means this column vector becomes row vector. Then y will remain as column vector. Then product x1, y1, x2, y2, so on xn, yn is called, is a scalar, which is, this is called as inner product space. Inner product. Okay. Right. So now this is the definition. When we take an example, it becomes very clear. Okay. We'll see it. Next is length of a vector. So length of a vector. Suppose x is a vector in V and C or V and F, right? x1, x2, so on xn. Then x transpose x, where it may be, if it is in case of complex, it is complex conjugate. Otherwise x transpose x, if we define, what happens, x1, x2, so on xn, that is the transpose. Then column vector x1, x2, so on xn. If we go for its inner product as discussed, x1 square plus x2 square, so on xn square, which is called as inner product of, it is called as inner product of x, right? It is inner product of x, right? Now if we take the positive square root of this inner product, right? So very simple, one vector x1 is there here, very simple, it is nothing but x1 square plus x2 square plus so on xn square is called as inner product. If we take the square root of this, right? So this is called as norm of a vector, so denoted by this. So norm of a vector is nothing but the length of the vector. Okay. So then if suppose x is a vector, we know its norm, right? norm is nothing but this, right? Then x by norm x, if we take, so this, if you find the length of this vector, that is norm of this, it becomes 1, then this is called as normal vector or unit vector. That means x by norm x is called as a unit vector. I think this is we are familiar with, right? In terms of vector calculus, this is what we do, right? A by that a bar, right, is called as a unit vector. The same here. So instead of this, what we say is x by norm of x. Norm is nothing but again length of the vector. Length of the vector is nothing but under root x1 square plus x2 square plus x3 square, so on xn square, right? So next is orthogonal vectors. Very simple. When two vectors, it may be real or complex, right? In case of real, it is a directly inner product, x transpose y equal to 0. In case of complex, it is x star y equal to 0. Again, it is inner product, but only thing is x star comes where it is transpose conjugate, right? So whenever this inner product equal to 0, right? So then the two vectors are called as orthogonal. Right? That is the inner product equal to 0. Inner product equal to 0 means this is suppose if you take only its same vector x comma x equal to 0, that is x1 square plus x2 square plus so on xn square equal to 0. Then the vector is called as orthogonal vector. Suppose if with respect to two vectors, one vector is x, other one is y, and its inner product equal to 0, then these two vectors are called as orthogonal to each other. Then orthogonal matrix. So if P transpose P equal to P into P transpose equal to identity matrix, then P is called as an orthogonal matrix. Then this another important with respect to examination, that is normalization of a vector. If x is a vector, then x by norm x is a normal vector. Or it can be like normalize the vector x equal to 2 comma 4 comma 4, or find the normal vector of x where x equal to 2 4 4. Right? Very simple. Immediately we have to find its norm. Norm is nothing but length of the vector, that is under root of x1 square plus x2 square plus x3 square, that is 6. Then x by norm x, that means 2 by 6, 4 by 6, 4 by 6, which is 1 by 3, 2 by 3, 2 by 3. Okay. Now if you want, you can verify here what is its length of this vector. If you find, so 1 by 3 whole square, 1 by 9, right, plus 2 by 3 whole square, that is 4 by 9, right, plus 2 by 3 whole square, that is 4 by 9, right. So 4 plus 4 8, 8 plus 1 9, 9 by 1 9, 1, that is 1. So once you normalize, the length of the vector becomes 1, right. So this is what we discussed. One is so in this video, in this session, what we discussed is rank of a matrix. Right? So basic definition of the rank, that is rank with the help of minors, that is with the help of determinants. Right? And other one is rank with the help of echelon form of the matrix. Right? So next is based on this rank. So what we tried is we try to find whether the given vectors are linearly independent or linearly dependent. Right? And third one is, so we define some terms like vector space, subspace, etc. Vector space, kind of discussion related to vector space in this. So here the important thing is, in this important concept that we need to focus is basis as well as dimension. So very, in terms of definitions as well as in terms of problems, it is very important to have this basis and dimensions. and other one is norm of a vector. For short answer, it is a regular thing that appears. Normalize the vector or find the norm of the vector, etc. Okay. So with this, we'll stop. In the next session, we'll discuss the rest. That is the two important ways or important concepts to find the inverse of a matrix, which is a new concept to us. Okay, thank you. So I think we'll stop with this for today.